Okay, so what we have here is question 16, and on question 16 we're asked to draw an Aragon diagram. Now, remember, if I draw a random complex number such as this, like 3 plus 5i, okay? What this represents then is that when I draw 3 plus 5i and I find the modulus of this complex number. So if I find out the modulus of this complex number and equals, 3 squared plus 5 squared, and that gets me the square root of 34. This means that if any other complex number is this distance out from the center, any other complex number here, they will all have a modulus value of root 34. So that's what that means. Any complex number on this circle, no matter where I put it, will all have a modulus value of root 34. Now, what we're going to look at next is basically what happens when we are given two moduluses. So we're given a range of modulus, okay? And the first says find a set of points where basically 1 is a smaller number than the modulus. So if I find out where 1 is, so we're just going to draw this on the diagram. That's going to be worth 1, that's going to be 2, that's going to be 3, it's going to be minus 1, minus 2, minus 3, and the same thing up, 1, 2, 3, minus 1, minus 2, and then that's minus 3 down there. So what's going to happen this time is a modulus of 1 would indicate that all the lengths are 1. Okay, like so. Okay, so they're all worth 1. Then 1 is smaller than all the moduluses. So any number in here, or any complex number in there, hasn't got a large enough modulus to be part of this set of numbers, because a set of numbers needs to have a modulus in between 1 and 2. So we're going to write down all the numbers with a modulus of length 2. So we go as far as 2, and these are the complex numbers that would have a modulus of 2 if we were to find that modulus out. So what we're going to do is, it's all the complex numbers we're allowed is all the points in between, all the points that have a modulus in between 1 and 2, and it's going to be this shaded region here. Any complex number in this region will have a modulus between 1 and 2. So even in here or in here, they'll all have modulus values in between 1 and 2. Okay, now we're on to question 18. Let's Z equal P plus Q, where P plus Q is element R, and I squared equals minus 1. If the modulus of Z is root 2, and the argument of Z is 3 pi over 4, find the values of P and Q. Well, that's pretty easy because it's given it to us in polar form. Okay, and polar form is written as R cos theta plus I sin theta. So it's R cos theta plus I sin theta. So in this case, theta equals 3 pi over 4, and the R value is, or the modulus value is root 2. So it's going to be root 2 bracket cos 3 pi over 4 plus I sin 3 pi over 4. You put your calculator into radian mode and multiply it out, and what you're going to get is going to be minus 1 plus 1i. So P therefore equals minus 1, and P and Q therefore equals plus 1. Okay, that's question 18 done. Now we're on to question 20. Now, question 20, let Z equal x plus yi, where x was element R and I squared is equal to minus 1. Show on the Aragon diagram a set of points such as Z minus 4, such as Z minus 1 minus 4i equals Z minus 5, and okay, so on the Aragon diagram. Okie dokes. So what we're first going to do is we're going to get Z minus 1 minus 4i. So we're going to write that down. So it's going to be x plus yi minus 1 minus 4i. And that's going to equal Z, which is going to be once again x plus yi. and then that's going to be minus 5. Now we have to get the modules of both of these, so we've got to break it up into real numbers. The real number here is going to be x minus 1 is the real, and the imaginary is going to be y minus 4i. It's the imaginary part. And in this one here, the real part is going to be x minus 5. It's the real part, and the imaginary part is going to be plus yi. That's the imaginary part. Now remember, these modulus signs here means the square root of the real squared plus the imaginary squared. So what we're going to get is we're going to get the square root of x minus 1 squared plus y minus 4 squared equals the square root of x minus 5 squared plus y squared. Now we can get rid of the square root signs right away and multiply this out to get x squared minus 2x plus 1. And this here equals y squared minus 8y plus 16. This here is going to equal x squared minus 10x plus 25. And this part here is going to be plus y squared. Cancel off what you can on both sides. The y squareds cancel, the x squareds cancel, and what we're going to get is 1 plus 16 is 17, minus 2x plus 17 equals minus 10x plus 25. Bring them over the other side and they're going to be plus 10x minus 25. And we're also forgetting about the minus 8y here. So what we're going to get next is we're going to get 8x minus 8y minus 8 equals 0. And what we're going to get is x minus y minus 1 equals 0. This is the equation of a line. So what we can do with this equation of a line is we can draw it on the Argand diagram. So what we might do here is just find 2 points on this line. So we draw this from here. So what we could say is when x equals 0, or what we say is x equals 0, we're going to get a minus y equals minus 1. So, minus y minus 1 equals 0. And then bring over the y and we get y equals minus 1. So that's 0 minus 1 is 1 point. And then the other point is when y equals 0, we're going to get x minus 1 equals 0 and x equals 1. So there's 2 points, 1, 0 and 0 minus 1. So if we draw this out, draw this out, we get a 1, 2, 3. We get 1, 2 and 3, minus 1, minus 2, minus 3. We get minus 1, minus 2. Let's draw this point out. So it's going to be the point 0 minus 1, which is located here, and then the point 1, 0. Then once we draw this line, we're going to get is this line here. So as we can see, there we go there. So let f of z be a half z plus z bar and I be a half I z minus z bar. Find f of z and explain the result. Okay, so what we're going to do this time around is we're going to write down the conjugate or z bar of x, which is going to be x minus yi. We're going to add them together, so we're going to get z plus z bar equals x plus yi plus x minus yi, and what we get is 2x. And then z minus the conjugate is going to be x plus yi minus bracket x minus yi, and that's going to get me 2yi. So what it wants me to do is wants me to get half of 2x and a half I multiplied by 2yi. So what we're going to get this time around is f of z therefore is going to be a half of 2x, which is x, a half I times 2y is going to be plus 2yi squared, and it's going to be x minus 2y is what f of z is. Oh, sorry, not 2y, x minus y. Excuse me. So, f of z equals x minus y. And x minus y is a real number, because it's the x value and the y value, okay? And it goes every complex number of the form x plus yi will be mapped onto the real axis at the point x minus y 0. Let me give you an example of what this means, okay? So, for example, if we were to look at the points on this graph here, okay? So this is the real and imaginary graph again, okay? And the real one, f of z equals x minus y. So for example, in part 2 we're going to get f of 3 minus 4i. Now 3 minus 4i is basically a real number of the x value is 3 and the y value equals minus 4. And what it says is, it says f of z is x minus y. So it's going to be 3 minus 4, which is going to give me 7. This is the value 7. So 1, 2, 3, 4, 5, 6, 7. That's where this is where f of 3 minus 4i is located. But remember, 3 minus 4i is located down here to begin with. So it gets sent on to the real axis. Okay? If we look at the second question, which is 5 plus 2i, 5 plus 2i is located 5 across and 2 up. This is 5 plus 2i. Now, once again, this time around we're looking for f of 5 plus 2i. And 5 plus 2i, x equals 5, y equals 2. Therefore, f of 5 plus 2i is the x value minus the y value, which is going to be 5 minus 2, which equals 3. And we can see that this point gets mapped onto 3, 0, or 3 plus 0y. So what it does is it maps a complex number onto the real axis. Okay, so its answers to that are 7 and 3 respectively. Okay guys, so that's the answer to question 20.